Okay, welcome to Math372 Complex Analysis. This should be Lecture 7. Thank you, and the solution key over there. All right, so what we're going to do today is we're going to continue with the reign of Cauchy. All right, so we ended last class by proving some really nice results. We proved that if we have a holomorphic function, and for those of you who are visiting from high school, in order to make the subject sound better, instead of saying a function is differentiable, we say it's holomorphic. Instead of saying a function has an antiderivative or an integral, we say it has a primitive. And it's just nice code language so that we can sound. So if our function is holomorphic in an open set, then our function is infinitely differentiable. And further, its value at any point inside the disk is given by integrating along a closed curve, we usually use a circle, of the function f of zeta over zeta minus z. So what is truly remarkable about this is it tells you that if your function is differentiable, there's only one way to fill it in. It's uniquely determined. And then we showed that the nth derivative of the function is given by the integral of f of zeta over zeta minus z to the n plus 1. The physics proof of this is to just interchange the order of differentiation and integration, just push the derivative with respect to z past the integral. That has to be justified. We justified it. Okay? It takes about half a class. The economics way is to just write it down. That's a little bit too short. But you can choose which level of detail you want. Okay? Now that we have this, it's highly suggestive that our function has a Taylor series expansion. And so that's our next theorem. The word holomorphic equals analytic. So I'm preparing my son for his spelling test today. He has words like advance. I would love him to have the word analysis and to write the word holomorphic. And the teacher mark it wrong. And my son, bring into his 5th grade teacher, look, holomorphic equals analytic. This is a valid spelling. There's a chance it could happen. All right? One direction is easy. Okay? We've already done this direction. Because what analytic means is you have a Taylor series that converges. Well, if you have a Taylor series that converges, we showed that you can differentiate a series that converges inside the radius of convergence term by term by term. So that direction is no problem. Okay. What's left is doing the other direction. So we want to show that if a function is holomorphic, it's analytic. And we have a candidate. So the idea is to do one of my 2 favorite things. So there's enough students here who have taken classes with me. What do I love to do? Multiply by 1. What else? And add 0. I basically like to do nothing. I get paid decently for it. Hours are nice. So do you think this is a multiply by 1 problem, or do you think this is a add 0 problem? So we're trying to write we're trying to do a Taylor series about z0. Say Taylor series about the point z0. So how would you multiply by 1? I want to get a z0 into here to have a z below. I have a zeta minus z. Yes?
You could add 0 on the bottom, so do zeta minus z plus z0 minus z0.
Yeah, so let's do zeta minus z is zeta minus z0 plus z0 minus z. And if I'm trying to do a Taylor series expansion about the point z0, z0 and z are going to be very close to each other. So if you think about it, here is my omega. Here's my point z0 that I'll expand about. Here's a little ball around it, and I'll choose z very close to z0. So I can write this as zeta minus z is zeta minus z0 minus z minus z0 with parentheses. Now, zeta minus z0 is going to be really small. Are we always expanding about the point 0? It could be anywhere, right? We don't necessarily have to have this. So z0, not. Sorry. So we can write this as zeta minus z0. Let's pull this out. And then you get 1 minus z0 over zeta minus z0. Okay? This is really small. Zeta minus z naught. Well, zeta is on the boundary of the circle. Z naught and z are really close to each other. I can make sure that z is very close to z naught, closer than the distance from z naught to zeta. What can you tell me about this fraction here? How large will it be in absolute value? Less than 1. So now what are you thinking of? Geometric series. I have this in the denominator. Right? So since this is in the denominator, I want to replace this here with its reciprocal and then use the geometric series. Have you guys seen the geometric series? 1 plus r squared equals 1 over 1 minus r. So this is one of the most important series we have. It converges beautifully. So now that we have that, what can we do here? Well, we know what f of z is. F of z is 1 over 2 pi I integral over c f of zeta. And now I'm going to substitute for 1 over zeta minus z. So I'll get a zeta minus z naught. And then I'll have a sum, n goes from 0 to infinity, of zeta minus z naught over zeta minus z naught to the n. And this is just from expanding the geometric series. I have the reciprocal of this, so I have 1 minus r. This is my common ratio r. I knew I would forget that at some point. That's why I put the smaller one first, because the smaller one will not fall off as well. OK. Now what do you want to do? We want to swap the integral and the sum. Right? The real hold-up in mathematics is justifying these interchanges. I think I've told you when I was a freshman, my physics professor told us one day, in math, it would take you 6 weeks to justify this step. Moving on, we see, and that's exactly what you should do in a physics class, so that you can get to the interesting applications. The math class, we're now going to justify that because it does not always work. So we want to switch the order of the sum and the integral. Now, one thing that makes this a lot easier is the geometric series is really nice that the tail of a geometric series is a geometric series itself. So we could actually sum all the way up to big N, and then what's left over is going to be a geometric series. Replace that with the infinite part, and then we would have a finite sum in an integral. We can switch a finite sum in an integral, and then you would just bound that the error is small, and then let things go to infinity. So that's one way to do it. Another way to do it is to know that this is less than 1 in absolute value. So this is geometrically decaying or exponentially decaying. Because our function is bounded, it's continuous, this numerator is bounded by some quantity. Zeta is a point on a circle centered at where? Where is the circle centered? It's centered at z. So technically, what we have here is z naught close to that, and then here is some circle centered at z where zeta lives. But we can make sure that z and zeta are so close to each other that this distance is always going to be bounded away from 0. So this is going to be bounded. The length of the curve is bounded. It's a circle of small radius. So everything converges absolutely. So the justification, the Fubini or the Fubini-Tunelli theorem to justify interchanging, got to be more careful, is if the sum integral, if the integral, if the sum of the absolute value converges, then you can interchange. And so this is a great result from real analysis. We can interchange. And now we get the sum, n goes from 0 to infinity, 1 over 2 pi I, integral over c of f of zeta, zeta minus z naught to the n plus 1. And then we'll put over here the z minus z naught to the n. And you can really see the Taylor series emerging now. Well, we actually know what the bracketed quantity is. That's just the nth derivative. The nth derivative where? At z naught, because we have a z naught down here. And so this is now the sum, n goes from 0 to infinity, of the nth derivative at z naught. But we have a 1 here. And over here on this board, we have an n factorial. So we have to multiply by n factorial and divide by n factorial. Oh, life is good, right? And there you go. Absolutely amazing. So I think we've now done all the bad parts of complex analysis. We can now integrate over any curve and not worry, have we only proven this for triangles? We now can use analytic and holomorphic interchangeably. And so now it's time to start getting applications of this. So I want to make sure we do some spectacular integration today. Okay? So the whole lie of Calc 1, Calc 2, Calc 3 is that you can integrate. In general, it's very hard to integrate. Okay. So we have a couple of consequences from this. So the first, as a corollary, is the Cauchy inequality. So conditions as above, the nth derivative at z in absolute value is less than or equal to, we'll do it this way, some constant depending on f over r to the n. So this follows immediately from this. The nth derivative is n factorial over 2 pi I. We'll take C to be a curve, a circle of radius r about the point z. So since it's a circle of radius r about z, this zeta minus z in absolute value is always going to be r. That's how far apart they are. So we get an r to the n plus 1 here. Because the function is differentiable, it's continuous. Because the function is continuous, it's bounded. So there's some bound here. We can pull that outside the integral. The length of this curve is 2 pi r. The 2 pi's actually cancel. One of the r's cancels one of the r's down below, so that's why we have an r to the n and not an n plus 1. We do have the n factorial, so this bound here is actually n factorial times the maximum value of the function. In almost every application I know, it doesn't matter what constant it is. It just matters that there's a constant. So this is true for all n. In particular, we have a bound on the size of our function. It's less than or equal to some, and here, I'll call that constant maybe CFN, because the constant can depend on n. It'll be less than CF0 over, how do I want to do this? I'll do it this way. The first derivative is bounded like this. Now, I have hidden something here. It's right, but it can be a little bit confusing. It's very easy to make mistakes and to be subtly assuming something you should not. Right now, I can actually prove that the only functions that are differentiable are constants. So the function f of z equals z does not exist, nor does f of z equals z squared. Later, I will prove the Riemann hypothesis for you, which is worth $1 million. If you make small little things, and this is why we have rigorous math classes. When I integrate, if I integrate from x equals 0 to 1, how do I write I integrate from x equals 0 to 1?
The integral sign up is 0 on the bottom and a 1 on the top.
No, that is not how I write it.
Oh, x equals.
Yes, yes, everybody else in the world writes 0 to 1. But Professor Miller, who owns a chalk company, writes x equals 0 to 1. I do not own a chalk company. I should really invest in one based on how much chalk I use. Why do I write x equals 0 to 1? So it's explicit what I'm integrating against. When I'm writing here my bounds, I want to write what the bound depends on. I'm saying the bound depends on the function and on n. Does the bound depend on anything else? In what sense does it depend on z? It depends on the size of the function on a circle of radius r. I really should have some r dependence in this constant. Because, for instance, if I have the function f of z equals z, the further out I go, the larger my radius, the larger the bound on the function will be. So if I write that it depends on the function, that's correct, but it also depends on the size of the radius. That's how it depends. Now, I could say I'm going to just use the maximum value of the function. Well, if my function is f of z equals z, what value would I have to use? Infinity. And so I would have the result that the nth derivative is at most, in absolute value, positive infinity. There are easier ways to get that result. This is why you really want to be explicit. You should really put in an r over here to remind you that it depends on the maximum value of the function on a circle of radius r centered at the point 0. So really, I should have something like this. Okay? So notation is extremely important. All right, let's see an application of this. So it's time to meet a mathematician other than Cauchy and other than Riemann. We will meet Liouville. Liouville's theorem. If f is entire and bounded, then f is constant. That's a nice theorem. So entire means that you are holomorphic everywhere. You're differentiable for all c in the complex plane. At every point, you're differentiable. The proof is actually remarkably straightforward. By Cauchy, we know that f prime of z is less than or equal to some constant over r. But what do I know about this constant? It has no r dependence. Because we're assuming the function is bounded. So there's some number that works no matter what radius we have. Therefore, f prime of z is less than or equal to some constant over r. And this is true for all r. Now let r go to infinity. So send r to infinity, get f prime of z has to be 0. So we've just shown that the first derivative is 0. We have a couple of ways we could go. We could now show that the second derivative is 0, the third derivative is 0. We could show all the derivatives are 0. And so that the only thing that's left is the constant term. Yes?
It seems like all that we've shown there is that the derivative approaches 0 as r goes to infinity. So how do we know that the derivative is?
Well, because if the derivative was not 0, it would have to have an absolute value strictly greater. So if the derivative is, 1 over how much I like the Yankees.
Yeah.
Well, actually, how much I like the Yankees, not 1 over. The reciprocal would be too large. So if it's the amount I like the Yankees, an extremely small number. Eventually, I would be so large that it would be smaller.
Yeah.
So is this enough to then just show, well, all the derivatives vanish, so the function just has to be constant? We know it has a Taylor series expansion. All the coefficients are 0. So this is one avenue of proof. The other is you have a function whose derivative is 0 everywhere. In real analysis, we would use the mean value theorem and say, well, look, f of b minus f of a is f prime at some intermediate point times b minus a. We sadly don't have the mean value theorem right now for complex analysis. So I will leave it to you to figure out, can you do this another way? But this is a terrific consequence of Cauchy's inequality. The only bounded functions that are differentiable everywhere in the complex plane are constant. This is extremely different than the real variable case. In the real variable case, let's see, we could consider the function f of x is 1 over 1 plus x squared, or f of x is sine of x. These are nice functions. They're bounded everywhere. They're differentiable everywhere. Functions like this do not exist in the complex plane. So if you take 1 over 1 plus z squared, as z approaches I, that's actually going to approach plus infinity. All right. So we've now proven Cauchy's inequality. We've proven Liouville. Let's look at a consequence of Liouville. So I'm going to put the high school students on the spot right now. Okay? Have you heard the word fundamental in any of your math classes? Okay.
Yes.
Okay. Can you name a fundamental theorem?
Root theorem.
Okay, what's the root theorem?
I don't know.
Okay. I'd call that a lemma, not a fundamental theorem. Fundamental is supposed to be really meeting the key result in the subject. So you should have seen at least 1, 2, or 3 of them by now.
Like the relation between like a function and its like derivative. Like
Good. Good.
Here, right?
The fundamental theorem of calculus. The area under a curve is equal to the antiderivative at b minus the antiderivative at a. That's the fundamental theorem of calculus. It merits the name fundamental. And areas under curves are typically probabilities. This is one reason why we care about it so much. You might have heard about the fundamental theorem of arithmetic. Every number can be written uniquely as a product of prime and prime powers, unique if you put the primes in increasing order. There's also one other fundamental theorem you might have seen in high school involving polynomials. The fundamental theorem of algebra. If I give you a polynomial of degree n, it has exactly n roots. Okay? So it's a very nice result. Now, complex analysis is extremely different than real. So if I give you a function, a polynomial with integer coefficients, does it have to have integer roots? No, if I give you 2x minus 3 equals 0, all right. So an integer polynomial does not necessarily have to have integer roots. Maybe a rational polynomial has to have rational roots. X squared minus 2 equals 0, x equals root 2. Okay? Polynomial with rational coefficients has rational roots. That's out. All right. Maybe real coefficients has real roots. X squared plus 1 equals 0. X equals I, which is or am the square root of negative 1. Okay, that's out. So what we keep seeing is that these sets of numbers that we're working with are incomplete. You can study functions, you can study polynomials over them, and you have to leave them to find solutions. Now, what's absolutely amazing is if we just take x squared plus 1 equals 0, that gives us 1 or 2 new roots, I and minus I. And that gives us the complex numbers. So C is the set of all numbers a plus ib, a and b are real. The fundamental theorem of algebra. A finite polynomial with complex coefficients of degree n has exactly n complex roots. So what this means is the polynomial fully factors. It means the complex numbers are closed. We don't have to keep adding more things. Just because I add the square root of 2 doesn't mean I can solve x squared minus 3. I would have to add the square root of 3. And if I want to look at x minus pi, I'd have to add pi. There's a lot of things I have to add. All I have to do is add just the square root of negative 1, and now no matter what I do, I can get all. So it's really worth thinking about what this means. Every finite polynomial with complex coefficients factors completely. It doesn't mean that it has distinct roots. If I was really generous, what polynomial of degree n would I give you? No. Extremely generous. X to the n or z to the n equals 0, right? Find all roots of z to the n equals 0, right? You would have the root 0 of multiplicity n. If I was slightly less generous, I would give you, x plus 1 to the n, because some of you might actually forget the minus sign, and you might say the roots are, 1 as opposed to minus 1 with multiplicity n. Notice what it does not say. It does not give you a procedure to find the roots. It doesn't say, oh, well, let me tell you how you find them. This is what you do. So we have the quadratic formula. There's the cubic formula. There's the quartic formula. And beyond that, nothing. We can prove that you cannot find a closed form solution for the roots of a polynomial of degree 5 and higher that always works using just radicals and sums, subtractions, multiplications, divisions. It's either a very beautiful theorem or a very disappointing theorem, depending on your point of view. There are numerical procedures to find the roots, or to find close approximations to them. A beautiful thing called Newton's method. This leads to a lot of fractal geometry when you try to see which root does this go to. And you can get things that are very close as starting points for your guess that iterate to very different roots. So there's a huge subject here that if we are interested in, we can look at later in the semester, complex dynamics. But it doesn't tell us how to find them. Okay. Any thoughts on what theorem might be useful to prove the fundamental theorem of algebra? Probably the theorem we just ended with a moment ago, right? Liouville's theorem is going to prove the fundamental theorem of algebra. So the first thing when you do all proofs like this is you always want to do reductions. Okay? If I have a finite polynomial, I claim I just need to find one root, and I'm done. And the reason is if we can find one root, we pull that root off, and then we have a polynomial degree n minus 1. So if you can find one root, you win. Okay? Okay. There are lots of different proofs of the fundamental theorem of algebra. There is a proof using just techniques from multivariable calculus, and I think using the some of the derivatives, and might use Lagrange multipliers, I can't remember. I will post the proof using the techniques from Calc 3 of proving this. Of all the proofs I know, this is the one I like most. There are some things you can try to do. You can say, for instance, if I have a polynomial with real coefficients and it's of odd degree, it has to have at least one root. Because it's going off to plus infinity in one direction and minus infinity in the other, because its leading term is odd. But then you get down to a polynomial of even degree, and a polynomial of even degree might not have any roots. If I give you the polynomial x squared plus 1 has no real roots. And then we get into trouble like this. All right, so proof of fundamental theorem of algebra. 1. Without loss of generality, enough to find one root. If we want to, what can we assume about the constant term of our polynomial? I'm sorry? 0. Well, if it's 0, if the constant term of our polynomial is 0, it would be like z cubed minus z. And then we would have a root. Z equals 0 would be a root. So if we wanted to, we can assume that the constant term is not 0, because if it's 0, we know a root, and we're done. And then, since it's not 0, we can rescale and make it 1. So if we wanted to, we could assume the constant term is 1. We don't need to, but it's just good to get into this process of what assumptions can I make, what simplifications can I make. Okay. Assume not, so f of z, well, I'll call it p of z, does not equal 0 for all z and c. And so I'll write f of z as, an z to the n plus a naught. And an does not equal 0. Okay. If z gets really, really large, which term matters most in this expression? The z to the n. So it could be the case maybe, and I have done some research with colleagues where things like this happen, where maybe, for example, it's 10 to the negative 14 z to the 100 plus 10 to the 88 z to the 99. So if you have something like this, 10 to the 88 z to the 99 is going to beat the crap out of 10 to the negative 14 z to the 100 for quite a while. But eventually, once z is sufficiently large, this extra z is going to dwarf this. Once z is greater than, say, 10 to the 88 divided by 10 to the negative 14. So eventually, this term will kick in. So what you need to just do a little carefully is show there exists an R such that for all z greater than R, the absolute value of an z to the n is greater than twice an minus 1 zn minus 1 plus a0, and I'll put absolute values. That eventually, this is going to be larger than all the other stuff. And in particular, it will imply some kind of decay. So now let's consider the function f of z is 1 over p of z is 1 over an z to the n plus a0. Whenever you see the reciprocal, you should be very concerned. What must be true for this to be well defined? Denominator has to be non-zero. Is the denominator non-zero? Good, we're fine. If z is sufficiently large, I know that the stuff over here, let's see, do I want a 2 there or do I want a half? Okay, I think I want it the other way.
Wouldn't it work?
Yeah.
For a 2 because it's
Yeah, it works for 2. Yeah, it's a stronger, yeah, let's leave it as a 2. So we know that this is never 0, so this is well defined. Is this function differentiable? Yeah. In fact, it's infinitely differentiable. F is holomorphic. It's entire. All we need to do is show that it's bounded, and then by Liouville it has to be constant. So we know if z is sufficiently small, it's going to be some value, it's not going to be 0. As z gets really, really large, we're dominated by the main term. This main term is going to infinity. So if z is really, really large, everything other than the main term can't be enough to subtract all of it away. And so p of z has to be at least a certain size. So 1 over p of z has to be going to 0. So we can choose r so large that this expression is at most epsilon. I'm sorry, so that this expression is at least epsilon in absolute value. So then this fraction is at most 1 over epsilon. So we can show it's bounded. So that's where you want to just go through and carefully put in the details. The actual algebra is in the book. It's a good exercise to go through and put the details in. But the main idea is that what's going on here by the triangle inequality, it can't be enough to subtract things off. And so, if I tried to do the triangle inequality, I would get, this is p of z over here. So what I would get is I would get the absolute value of p of z is greater than or equal to an z to the n minus an minus 1 zn minus 1 plus a0. I'm basically trying to assume that there's as much cancellation as possible. And we know that this has to be a certain size. So we get that f of z is bounded. And the reason is, choose a circle of radius r so that this is greater than or equal to epsilon if we are sufficiently far away. So then outside this circle, we're at most 1 over epsilon when we're looking at f. Inside the circle, well, the function f is continuous. And we know a continuous function on a closed bounded set attains its max and minimum. So now we know our function is constant. Okay? So by Liouville, f of z equals 1 over p of z is constant. That means p of z is constant. The only way a polynomial can be constant is if an equals an minus 1 equals a1 equals 0. This contradicts the fact that we're starting off with a polynomial of degree n. So a polynomial has a root. And once it has one root, we just iterate this n times, and now we have a factorization. So this is the fundamental theorem of algebra. Every polynomial of degree n has exactly n roots. Okay? I'm going to skip the points of accumulation right now. When I was looking at my notes, I goes, why did I skip that back in 2015? And I was, oh, yeah, because if I do points of accumulation, we can't do an integration. And so we will postpone points of accumulation for now. Some of you will have an unfair advantage on this problem. let's integrate from minus infinity to infinity of dx over 1 plus x squared. This is possible to do with high school mathematics. Or Calc 1. Have you seen this? Okay, what's the answer?
I don't know, but I've seen it.
Okay. Do you remember what it involves?
Inverse?
Yeah, arctangent of x. The derivative of arctangent of x is 1 over 1 plus x squared. I don't think I'll have enough time to get through this today as to why that you know. Wait, it's only 36? Oh yeah, we have time. Do people want to see this? We have time. Okay, so the derivative of arctangent is 1 over 1 plus x squared. So when we integrate this, we're going to just get arctangent at infinity minus arctangent of minus infinity. Okay, so the rule we use is, imagine you have f of g of x equals x. So f and g are inverse functions. Then f prime of g of x times g prime of x equals 1. So g prime of x is 1 over f prime of g of x. So the point is to try to find functions that pair up nicely. So if I want to find the derivative of arctangent, I need to find a function that when I apply that function, when I evaluate that function at arctangent of x, I get x. So I want a function which at arctangent of x equals x. So arctangent means the angle that is the arctangent of x is the angle whose tangent equals x. So if you just read it, I take the tangent of arctangent, and I'll just get x. So arctangent prime of x is 1 over tangent prime at arctangent of x. All right. So let's take an angle theta whose tangent is x. What does it mean to have tangent of x? Well, that means this side is x, that side is 1. That's one way to do the triangle. The hypotenuse would then be 1 plus x squared. What's the derivative of tangent? Secant squared. Okay, and you can do this using the quotient rule. Excellent. If there was any compassion in naming mathematical things, cosine would go with cosecant and sine would go with secant. We don't do that. Yeah, we have to have some kind of weeding process. So 1 over secant squared is what we would now have, which is really just cosine squared. So this is just cosine squared of arctangent of x. Well, what's the cosine of this special angle? 1 over, oh sorry, this is a square root here. The cosine is just 1 over square root of 1 plus x squared. So since I squared this, it's just 1 over 1 plus x squared. Amazingly, in calculus, it's often easier to evaluate integrals from minus infinity to infinity than to find the indefinite integral. And now we can use this, and when you go through the algebra, when all the dust settles, you're left with pi. Okay? So we are able to do this. So if I show you how to do this with complex analysis, it's not that impressive. All right. But if instead of doing it with 1 over 1 plus x squared, if I did it as 1 over 1 plus x to the 4th, that's now impressive. That you do not know how to do using just calculus. What if I did 1 over 1 plus x cubed? What if I gave you that? Would you be impressed if I could evaluate this integral? Any concerns with this integral? Yeah, it blows up at -1. I'd be really impressed if I could evaluate myself. Right? I'm not going to be able to evaluate that one. What could I do so that I could evaluate this, or have a chance to evaluate this?
Separate it into two integrals that have the intersections at -1.
But I'm still having something that's blowing up. I don't want to have an integral that's blowing up. So just start at 0, or put in an absolute value. So if I just start at 0, now I have a chance of being able to evaluate this. It's going to decay sufficiently rapidly. And the original integral going from minus infinity to infinity, well, the way I can evaluate that is I can just double it from 0 to infinity. So it all comes down to I want to evaluate integrals like this. If n is even, it's a little bit easier to do than if n is odd. What I will do is I'll do n equals 2 just to keep the board work a little bit clean. Also, we know what the answer is when n equals 2, so we can check and see that it works. It will be extremely easy to generalize this to n equals 4. In real variable techniques, I have no idea how to generalize the arctangent result to n equals 4. So let's consider the following. So I need to choose a contour and I need to choose a function. So what function do you think I should take for my function f of z? 1 over 1 plus z squared. And for those of you who are joining us from high school, it's really more convenient if you could come to all the previous lectures so that you know the results. So when you enroll here, we'll expect you to attend more lectures. So this part is a beautiful theorem from complex analysis that converts integration to algebra. So we're going to use whose theorem? Cauchy. I mean, we used Liouville's theorem a moment ago. We can't have 2 consecutive theorems with neither one being Cauchy this early in the semester. I mean, that would just be ridiculous. So we need to choose a contour. Where does this function blow up? At where? At I and? At negative I. So I'm going to choose this as my contour. I'll choose a circle of radius r. And then here is I, and here is minus I. So if we look at what's going on, there is one point where it blows up. So what I could do is I'll do a contour like this. So I'll come along, and I'll go along this point counterclockwise. I'll then take the limit as this thickness goes to 0. Because I'm going up and down on the same vertical path, they'll cancel. And I get the integral over this whole contour. In the limit, it's going to be an integral along this side, the integral along the top, and the integral along this. And my function is going to be holomorphic in the region in between, so I'm going to get 0. So I get, by Cauchy's theorem, 0 is 1 over 2 pi I integral minus r to r plus the integral over, we'll call this the semicircle of radius r, and then plus the integral over, we'll call it the circle of radius epsilon, and I'll put a minus sign because we're going about it the wrong way. So, for those of you joining us from high school, I apologize. This is a major result that took several weeks to, well, actually I guess only about 2 weeks to prove. But it's a major result that a lot of integrals are 0. So now we can bring this integral over to the other side. And so we get that 1 over 2 pi I, the integral from minus r to r of our function, which is just going to be 1 over 1 plus x squared dx, is equal to 1 over 2 pi I integral over SR plus the integral over C epsilon. Oh, I'm sorry. And these two are together, and they equal this one. All right, now let's think about this. This is a circle of radius r. When you look at 1 plus z squared, approximately what is the denominator?
Z squared.
Approximately r squared. Right? The worst possible case for us is if it's such that z squared is minus r squared. And then in absolute value, this would be r squared minus 1. So the value of this function in absolute value is at most 1 over r squared minus 1. The circle has perimeter pi r. So this piece over here is going to be less than equal to pi r over 2 pi r squared minus 1 in absolute value. And that goes to 0. Okay? So now we're just left with integrating the function 1 over 1 plus z squared about a circle of radius epsilon about the point z equals I. Okay? Is this function holomorphic on that circle, inside that circle? No. So all we want to do now is we want to Taylor expand z 1 plus z squared. And we want to expand it about what point? All right, so we have to somehow write 1 plus z squared, expanding it about that. Well, let's see. We have 1 plus z squared is z minus I, z plus I. Is that right? So 1 over 1 plus z squared is 1 over z plus I, 1 over z minus I. If I'm very close to z equals I, this function looks like 1 over 2i. That's fine. This function blows up. I now need to do the Taylor series expansion of this. Done. Right? I want to expand this about the point I. Done. So now, what do I get? So 1 over 2 pi I integral over the circle of radius epsilon. So I have z minus I. Now I want to expand z plus I. Because all that really matters is the first coefficient of this. So I can write this as 1 over z minus I plus I plus I. I'm going to do this really pedantically. This is 1 over 2i minus z minus I. I'll pull out the 2i. It's 1 over 2i. And it's 1 over 1 minus z minus I over 2i. It's 1 over 2i. Now I use the geometric series. It's 1 plus z minus I over 2i plus z minus I over 2i squared. We get to use the geometric series again. So now when I put in this extra z minus I, all I care about is the 1 over term. This term is going to just give me the integral of 1 over 2i squared. That has a primitive. It just integrates to 0. Integrates to 0. Integrates to 0. The only thing that survives is the 1 over 2i. So it just equals 1 over 2i dz. And so we know that the integral of 1 over 2 pi I, 1 over z minus I about the point I is just going to be 1. So this just gives us 1 over 2i. And so we get 1 over 2 pi I, the integral from minus r to r, of 1 over 1 plus x squared dx is equal to 1 over 2i. The 2i's cancel, multiply through by pi, and there's our result. So the whole point was to get a good Taylor series expansion of this function. We want things in terms of z minus I. So I just need to write this other piece, the z plus I, like that. Yes?
When you, on the right side, between lines 1 and 2,
Right here.
should it be 2i plus z minus I?
Could be. Yes, it's 2i plus. Yes.
So then,
Yeah. It's yes. It's not going to change the answer, but you're absolutely correct. It should be like that. Yes. You can tell how much I care about that part of the algebra.
What's like that oxidation?
Oh, so in mathematics, we write a square that's filled in to denote QED, quo erat demonstratum, that which was to be proved, to just indicate we've reached the end of a proof. So that if your mind is wandering a little bit in the lecture, you can now realize, oh, he's moving on to something else, she's moving on to something else. Okay. So if you look at this, where did we really use the fact that we had the function 1 over 1 plus z squared? If I replace this with 1 over z to the 4th, 1 over z to the 6th, 1 over z to the 8th, I still have the same decay over here. All that changes is I now have more possible candidates. And I would just have more dots in here at the roots. It's not that bad. We can get 1 over 1 plus x to the 4th without really that much more trouble. Now, if I do an odd number, it's different. Because now I'm no longer going all the way off to minus infinity. You have to do something a little bit clever for an odd number. And so we will show that cleverness probably on Monday. If not on Monday, then on Wednesday. So a lot today, but the subject is beginning to come together. We proved a fundamental theorem today. We proved a really nice classification of entire functions, they're constant. And we showed how we can do some extremely difficult integrals that took clever observations in Calc 1 or things that couldn't be done in Calc 1, and now we've reduced them to just finding the negative first Taylor coefficient. I don't know about you, but I would much rather just do some algebra on the board. Yes, I might make mistakes, but I'll make mistakes in ways that don't matter. All right, so this is probably a good place to stop.